Good day, everyone. So here is my um, final PIT for numerical methods, which is Gaussian Quadrature. So Gaussian, as you can see in the my Gaussian Quadrature code, there is an import NumPy and SymPy for calculations and necessary libraries, and also Streamlit necessary for Streamlit Streamlit, and also SymPy parsing for the implicit multiplication, so that the user don't need to use star when using implicit multiplication. And it also have a function at the line 7 block of code. We have a function map used in mapping function mapping function in SymPy. And in this block of code, we also have a Gaussian quadrature, which is the one necessary for calculating the Gaussian quadrature. We have here for the nodes and weights of negative and 1, negative 1 and 1. And also we have these two for transformation of the interval a and b, which is depending on the user. So this formula is based from this formula in the book. So x b plus a plus b minus a x over 2, which is this b minus a over 2 means x row, then b plus a over 2. And we also have the w map, which is from this formula also, b minus a over 2 dxd. So after we map and we have an approximation, we will have the steps for row nodes, x row, row weights, and so on. And here we have the for the display. So Gaussian quadrature calculator. Here is for the user input, variable for the user input, f snake case str a b and n is for also the number of quadrature points, which is n, that we will be used here in Gaussian quadrature block of code. And also the a and b. We also have the x sp symbol used for SymPy, NumPy, and for calculation. And for user, this is also for the user input, so that the user, just like I said before, will not need to use the asterisks for putting the function. And also we have lambdify, necessary for lambdifying the numerical evaluation, and also the calculation of the result. So we have here the results and step for the Gaussian quadrature. We will call the Gaussian quadrature block of code, Gaussian quadrature function FABN, and this will display the steps taken after the results, also the steps taken. So the approximate is the result, and also the steps is here. So Gaussian quadrature node standard -1, it will display also the steps taken, and it also have a function plot using this st.write function plot that has xvals and yvals, and also an error exception for error that will be done by the user. So if we try to run the code, streamlit run app.py, and here is now the ang itsura sa code. So we have here a function plot, also the lower limit integration, which is a, and also the upper limit integration, which is the b, and also the n here, which is the quadrature points. So for testing the Streamlit, we have to find the problem. So let's try to find a problem here in in the book using this 2-point Gaussian Legendre. So we have here an example of 0.2 plus 25x plus 200x squared plus 675x cubed plus minus 900x to the power 4 plus 400x to the power 5. So we now have here the problem. So we will just need to on the lower the A, input the A and also the B. So the A of this problem is from 0 and the B is 0.8. So A is 0 and B is 0.8 using 2 points. So we have to use 2. Then after we use calculate, we were given the approximation, which is 1.822578. So this should be the same approximation in the book. So the approximation in the book is also 1.8.22578. So here at the function, you don't also need to put asterisk, because we already fixed that in implicit multiplication at the code. So even if the user didn't put asterisk, but they also need to put asterisk for exponent for expressing exponentials. So if we hit enter, then calculate, the result is still the same. And next we will have another example, which is using now a 3-point Legauss quadrature with the same problem. So if we change this into a 3-point, the answer should be, the approximation should be close to 1.640533. So if we calculate, and indeed the approximate value is closer to 1.640533. So here we can also see the steps taken. So we have the standard interval from -1 to 1, so which is -0.7746, 0. And also we have the weights. We also have the transformed nodes, so interval AB, and also the transformed weights and function values and weighted function values, and also the function plot. So even if we put 2 here, the steps taken will also depends on the input, the input the user put, and also the steps taken for solving that Gaussian quadrature. So we can also have our final quadrature, which can also use this problem. So 5x e -2x dx following integral, and we have to find the 2-point Gauss quadrature. And here at the using the next problem, we inputted another problem. So 5x e raised to the power of -2x with the lower limit integration a and the upper integration 1.3, 0.1 and 1.3 based on this problem. So we are expected to use the 2-point Gauss quadrature and estimate the value of the integral. So we have to use the 2 number of quadration points, or n. So if we use calculate, we are expected to see the approximation 0.9101018. So if we hit calculate, we can see the approximate value is still 0.910183. So here is a step-by-step summary. So we have here the Gaussian quadrature interval -1 to 1. We have the Gaussian quadrature weights 1 to 1. Transform nodes from interval a to b. So what is the transform nodes from interval a to b? and also the transformed weights, which is 0.6 and 0.6, and the function values of the transformed nodes and the weight function values. So it also here graphs the image of the graph, displays the image of the graph. And that's all for the Gaussian quadrature calculator, and thank you.